One of the many applications of passive microwave is the determination of surface wind speed. This module will briefly look into how wind speed is derived from microwave brightness temperatures, and we will also take a look at passive radiometer that can estimate surface wind direction in certain conditions as well. The background image is from a previous module and shows an example of surface wind speeds derived from a passive sensor. As we've seen before, the emissivity of the ocean's surface depends on the incidence angle of the emitted radiation and the frequency at which the radiation is emitted, as seen in this left panel. The emissivity is also dependent upon the polarization, vertical or horizontal, with emissivity of vertically polarized radiation increasing as the incidence angle increases, and that of horizontally polarized radiation decreasing. Wind speed dependence also exists, and is a function of incidence angle as well, as seen in the panels on the right. The pink box represents incidence angle at which typical passive microwave radiometers operate, and the figures show brightness temperature at 19.4 gigahertz as a function of incidence angle and wind speed for a fixed surface temperature. The dashed line in both panels represents a smooth, calm ocean, and solid lines represent various wind speeds, and this top panel increasing as we go up from this dip. At typical viewing angles viewed by passive microwave instruments, here in this around 50-degree range, maybe a little bit higher, emission of vertically polarized radiation by the ocean does not change as a function of wind speed. However, horizontally polarized radiation is emitted more as the wind speed increases. If other properties of the sea surface and atmosphere are known, this fact may be leveraged to help derive wind speed. Such sensors can estimate wind speed based on brightness temperatures in vertically and horizontally polarized channels. However, they are not able to retrieve wind direction unless fully polarimetric data and under certain conditions, such as high wind speeds and with low cloud cover. Only frequencies that can reliably see the surface are used in passive wind speed retrievals, such as 19, 37 GHz, or even lower. A high-frequency channel such as 92 GHz on SSMIS would not detect emissions from the surface in places where water vapor concentration was high, such as in the tropics. Therefore, it would be useless for deducing surface properties. WindSat is an example of a passive microwave radiometer that can derive wind speed and direction. It was designed by the Naval Research Laboratory Remote Sensing Division and launched in 2003 as part of the Coriolis satellite. It is still active as of 2020 and is the oldest multispectral polarimetric microwave radiometer in orbit. WindSat operates at 5 frequencies, which we'll see momentarily. Shown here is the ocean emissivity as a function of wind speed for one of those channels, 6.8 GHz. The top in both panels, the top and bottom sets of lines represent horizontally and vertically polarized emissions respectively. The y-axis denotes the change in emissivity caused by wind relative to some background state with no wind and a fixed sea surface temperature. A strong 30 meter per second wind, highlighted in this circle, would increase the ocean emissivity for 6.8 at the horizontal by about 8%, and in the vertical polarization by about 5%, relative to the background 290 K. Although that background emissivity would be something like 0.4 to 0.6, so those percentages are actually probably a little higher. Generally, emissivity increases as a function of wind speed for both polarizations. However, at low wind speeds, as we can see over here on the right in particular, ocean emissivity of vertically polarized radiation experiences a small decrease before again increasing. The 5 frequencies used by WindSat are 6.8, 10.7, 18.7, 23.8, and 37 GHz. Recall from a previous module that the 6.8 GHz channel is quite sensitive to SST, and the 23.8 GHz channel sits along a water vapor absorption band. These two frequencies can therefore be especially used to determine the effect of SST and tropospheric humidity on brightness temperature, while the others are then used for estimating the wind speed. Because the lower frequencies are not as heavily scattered by rain, WindSat can provide some estimates of coarsely resolved wind speed, even in places where precipitation occurs. Full polarimetry, which involves detecting vertically and horizontally polarized radiation, in addition to slant polarized and left and right-hand circular polarization, is used on WindSat. Passive observations can be used to determine wind speed in one of two ways. One, by detecting horizontal and vertical polarization from various angles, or two, obtaining a fully polarimetric single view of the scene, which is limited at estimating wind direction where the surface wind is light. An example of WindSat wind speeds during an incomplete day of observations is shown here. WindSat is in sun-synchronous orbit, so ask yourself, is this a set of descending or ascending orbital data shown? By zooming into some sector, we can now see wind vectors derived from the fully polarimetric data. And again, these are color-coded, where the warmer colors represent stronger winds, and you can see basically southwesterly or westerly winds in this scene. An additional, but very different method of detecting surface wind speeds over ocean is using Bistatic Scatterometry. This involves the use of a satellite instrument that, unlike traditional scatterometers, does not transmit its own signal. Instead, it deflects reflected GPS transmissions off the surface. Given that the GPS satellite location is known, and if we know the power transmitted by GPS, and then the location of the satellite doing the receiving of the signal, we can use scatterometry, the focus of a different module, to estimate both wind speed and direction without need to transmit a different signal. One limitation of this method is that if the GPS transmitted power changes unexpectedly, the retrieval to estimate wind speed must be recalibrated. The Cyclone Global Navigation Satellite System, or Cygnus, is a current example of bistatic scatterometry, and a schematic for one of these satellite platforms is shown over here on the right. The GPS signal, which is in the L band over here on the absorption spectrum, is not impacted by water vapor absorption and minimally by liquid water. Therefore, unlike traditional scatterometers, or even passive radiometers in some cases, Cygnus satellites can detect wind speed even in heavy rain, such as in tropical cyclones from low Earth orbit. And just to clarify here, we're looking at the wind speed and direction at the surface. Just to visualize this, a Cygnus satellite consists of only a receiver that detects some radiation that is reflected off the surface and transmitted by a GPS satellite in semi-synchronous orbit. Not shown here is the full Cygnus constellation. It consists of 8 identical satellites to help improve the temporal resolution of the data, as well as the spatial resolution. One example of Cygnus data is shown here on the left in an Atlantic tropical cyclone. For each panel, the blue line represents aircraft-based microwave estimates of surface wind in a cross-section through the storm. And the green line represents what the Cygnus constellation of satellites would see in the same location. And we can see this in 3 different cross-sections. Generally, the two agree closely. The panel on the right shows several passes through a West Pacific typhoon over a 3-hour-long period in this black box, and zoomed in up here to the top right. Strong winds can be seen at the center of the tropical cyclone, which is difficult for traditional scatterometers to do effectively because their signal is at least partially attenuated by scattering by liquid water. Like active sensing scatterometers, the radiation detected is reflected off of a large area, and the wind speed retrievals are somewhat coarse in spatial resolution, typically about 25 by 25 kilometers. More details about scatterometers that use active sensing techniques are included in a different module.